Hey everyone! Today, we're diving into some groundbreaking science that could revolutionize various fields, from medicine to 3D printing. We're talking about an innovative method developed by researchers at EPFL for moving objects in uncontrolled environments using sound waves. Welcome to Trendstorm. Chapter 1. The genius behind it. Back in 2018, Arthur Ashkin won the Nobel Prize in Physics for inventing optical tweezers, which are laser beams that can manipulate microscopic particles. While optical tweezers are incredibly useful for biological applications, they require extremely controlled conditions to work. Dr. Romain Fleury and his team at the Laboratory of Wave Engineering at EPFL have been working on a solution that overcomes these limitations. Their method, known as wave momentum shaping, uses sound waves to move objects, regardless of the environment or the object's physical properties. All they need to know is the object's position, and the sound waves do the rest. Chapter 2. How it works. Fleury explains that unlike optical tweezers that trap particles, their method gently pushes objects around, similar to how you might guide a puck with a hockey stick. Funded by the Swiss National Science Foundation, SNSF, SPARK program, this research has been published in Nature Physics and was conducted in collaboration with researchers from the University of Bordeaux, Nazarbayev University, and the Vienna University of Technology. Chapter 3. The experiments. Imagine a floating ping-pong ball on a tank of water. In their experiments, an overhead camera captured the ball's position while speakers at either end of the tank emitted sound waves to guide the ball along a predetermined path. Microphones listened to the feedback, called a scattering matrix, which, combined with the camera's data, allowed the researchers to calculate the optimal momentum of the sound waves in real time. This method, rooted in momentum conservation, is extremely simple yet highly effective. What's exciting is that this method isn't limited to spherical objects. The team successfully controlled rotations and even moved complex objects like an origami lotus. They also tested the system with both stationary and moving obstacles to mimic dynamic, uncontrolled environments, similar to conditions inside the human body. Chapter 4. Biomedical applications. Sound is a particularly promising tool for biomedical applications because it's harmless and non-invasive. Fleury mentions that some drug delivery methods already use sound waves to release encapsulated drugs. This technique could be especially useful for pushing a drug directly toward tumor cells, avoiding the need to touch or damage delicate tissues. Chapter 5. Beyond medicine. Beyond medicine. This method could revolutionize biological analysis and tissue engineering, where touching cells can cause damage or contamination. It also has potential applications in 3D printing, for arranging microscopic particles before solidifying them into objects. Chapter 6. Future goals. The researchers are now looking to take their experiments from the macro to the micro scale, using ultrasonic waves to move cells around under a microscope. They've already received funding from the SNSF to continue this exciting work. This innovative method of using sound waves to move objects in uncontrolled environments is a game changer. Whether it's advancing medical treatments, improving 3D printing, or making new strides in biological analysis, the possibilities are endless. Source: École Polytechnique Fédérale de Lausanne, EPFL. If you found this video fascinating, don't forget to like, comment, and subscribe. Share your thoughts on how you think this technology could be used in the future. Thanks for watching, and see you in the next video.